Hello everyone, Cristian here, and today I would like to present you our work Catch-22 uncovering compromised hosts using SSH public keys. This is a joint work with Anja Feldmann and Tobias Fiebig from Max Planck Institute for Informatics and Georgios Smaragdakis from TU Delft. Alright then, SSH or Secure Shell was firstly introduced in 1995 and it was a new protocol to be in exchange for the telnet, and the main purpose was to be used in a secure connection towards a remote machine. Nowadays it became really popular and there are more than 40 million machines out there that run SSH server. Now because of that, SSH became a really popular target for malicious actors, and malicious actors would very much like to get access through SSH. This is mainly for two reasons. One is because of the access, and secondly is because of the control of the machine that they get via the SSH. All right, so how would they do that? In here, we have a small example of an installation of a public key to gain persistence that we caught in one of the honeypots we are collaborating with. And as you can see, the malicious actor, after gaining access through brute force, installs their own public key in .ssh/authorized keys file for persistence. All right, so the question is, given the situation where we have these honeypots or we have malicious files that install these public keys, having the public keys, can we identify these compromised systems on the internet? And to answer this question, let's have a quick look back, a recall on how SSH handshake worked when we try to log in with a public key. So here we have a sequence sort of diagram. On the left side we have the client, on the right side we have the server, and we can see that after the TCP handshake and after the client and the server exchange their versions and the initial key exchange, the client can start an initialized authentication, sending a message user authentication request. Now, this request has two parameters. One is the username they're trying to log in into, and the second one is the hash of the public key, right? They're trying to use. Now, for this, the server will reply back with a challenge for that public key, and to authenticate itself, the client will use the private key to solve the challenge and will reply back with the proof back to the server. All right, so what's important here is that in case the client sends a public key and the server does not recognize that public key, the server will actually send back an error message. And this is an intentional design to be like this, because otherwise it actually enables a DOS attack over SSH, meaning that clients can just simply send various public keys to the server, and the server will have to compute a challenge for every one of them. And this is definitely something we don't want. So because of that, we can state, and that is the default behavior of the SSH, that the client will receive a challenge for the public key only when that public key actually exists for that user on the server. And this was firstly noticed in one of the blog posts in 2017 regarding the GitHub username and the public keys. So we kind of took the idea from there and we scaled up on all SSHs. So how would our scan tool look like to find this compromised host? We use the ZMap to scan for open SSH ports, and we patched the zgrab2 client, and we used it as an SSH client. And the idea is that the zgrab2 will be the one that will send that message user authentication request, right, for the user and the public key. And once receiving the challenge, we can stop the connection. So we actually never perform a full authentication handshake. But what's important here is that we're not gonna simply test malicious keys, but before testing the malicious keys, we're gonna send something that we call a canary key. Now, the canary key is a newly generated key, and the purpose of the canary key is the following. If the server accepts this canary key, which it's supposed it should not, then we consider this server misconfigured, right? Or it might be a honeypot. But either the case, we can not longer say anything regarding the compromised status of the server if the malicious key hits. So if the canary key got a positive hit, then we are not even considering that IP, that host, to test with the malicious key. Good. Before we go onto the internet and do actual scanning, we need to make sure that our tool will work on various SSH software. And for this, we did a series of in-lab testing, and we took the most popular SSH server implementation, OpenSSH, Dropbeer. We also found Bitwise SSH and Wolf SSH. As you can see, we tested all possible or all available to us versions of these tools. So for OpenSSH, we went from 9.4 until 2.1. For the Dropbeer, the same 0.84 to 0.23. In Bitwise, all versions that could be found from version 9 to version 6. And 1.4 for Wolf SSH. The takeaway here was that our tool worked without any problem on all the versions that were deployed after 2005. For the versions deployed previously or very like 20 more than 20 years older versions, our tool doesn't work, and this is usually because of the SSL libraries and the old ciphers, right? They don't match anymore. Okay, so next, before going into scanning, we made sure that our scans are ethical, right? And for this, we follow the Menlo report to the letter. So we had a rate limiting in place, not to bother the system administrators. We had a block list in case anyone wants to opt out. We were available 24/7, both on the phone and on the email. We set up a project webpage where we explained everything that what we're doing for this project, and we also set up a suggestive reverse DNS entry. In addition, we got also an IRB approval from our institution. Okay, good. The tool is set, ethics are done. Now, what are we scanning for? We need malicious keys. And for this, we got a nice collaboration with Bitdefender. And Bitdefender was kind enough to share with us a set of known to be malicious public keys. These public keys were collected in their honey traps, honey pots, the IR investigation from their clients. So as a matter of fact, we can and do consider these public keys known to be malicious because they were part of some malicious activity, a virus, a ransomware, and so on. So here in the plot, we have the activities seen by the Bitdefender of the top 52 malicious public keys that we were also using for our scans. We see that some keys on the bottom, so for example the key 1 to 10 are spread more over time. We see they're being active more over time, and we see a lot more counts of them compared to the others. All right, so going towards our experiment, this is what we did. We scanned the port 22 and 2222. We checked for free usernames, root, admin, and udatabase, and these are the usernames we also got from the Bitdefender dataset, basically being in pair with these keys. We use 52 known to be malicious public SSH keys. We scan for both IPv4 and IPv6, and for the IPv6 we use the public IPv6 hit list. Our scan started on 4th of April 2024, and they are still ongoing. So what we found is that we can identify compromised hosts in the wild. And as you can see here, our scans on port 22 and 2222 between April and August 2024 revealed more than 21,000 hits all over the world. Now, As expected, more compromised systems are in the countries with more robust and solid IT infrastructure, like China, US, European countries like Germany, Netherlands, France. There is also Brazil, Russia, Japan, India, and so on. So, what we did with all of these hits, again, prior starting our scans, we set up a collaboration with Shadow Server Foundation so we can send them this flow of the compromised IPs in the wild, and they will handle this notification to all the system administrators. So they created something called a special report on compromised SSH hosts, and there any system administrator can just subscribe and they will get notification if any of the IPs inside of their network was labeled as compromised. So did that help? We have here a very nice case of a European hosting provider where we see during our first scan that we got 152 hits on both username admin and root. There are multiple hits that or multiple keys that got a hit in this hosting provider, but on the second scan, after the notification went out, we see that this number was dramatically reduced to 36 hits and probably went reduced afterwards. All right, so jumping to the conclusion, what we showed in our research is that using the SSH protocol, using its RFC design, we can design a tool that can find compromised SSH servers in the wild simply using the known to be malicious public key. And through our extensive scans, we found more than 21,000 compromised hits all over the world. Thank you.